When Voyager 1 crossed the hidden edge of our solar system, something strange showed up in its readings. Out there, past the sun's protective bubble, space itself seemed to get thicker. The number of charged particles floating around the spacecraft started going up. 6 years after that, its sister ship, Voyager 2, saw the exact same thing happen. Right now, at this very moment, both of these machines are still flying, moving further and further into the empty space between stars. Their trip will go on for so long that they will outlast their builders, and maybe even outlast the stars we see in the night sky. But there is one thing about this whole story that still amazes me every time I think about it. How on earth are we still getting signals from them? These are machines built 50 years ago. They are now tens of billions of kilometers away from home. How are they still able to send us information about strange discoveries like this happening right now in real time? This story starts with an incredibly lucky coincidence. Back in the mid-1960s, a young researcher at NASA's Jet Propulsion Laboratory was working on orbital mechanics when he spotted something amazing. In the late 1970s, 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, were going to line up in a very special way. Each planet moves around the sun at a different speed, so an alignment like this only happens once every 176 years. Before that point in history, humans simply did not have the technology to travel that far. And once the planets drifted apart again, the opportunity would be gone. It was a once-in-a-lifetime window, and it would not come back for almost 2 centuries. Here's the tricky part. You cannot just fly straight through space the way a car drives down a road. Everything out there is moving in curved paths, constantly pulled by gravity. To reach a faraway planet, a spacecraft cannot simply point itself forward and go. It has to keep adjusting its path the whole way, and that takes a massive amount of energy. At that time, humanity did not have rockets strong enough to carry enough fuel for a straight shot to Neptune. Flying there directly would have taken a painful 30 years. But this rare planetary lineup opened the door to something called a gravity assist. Think of it like a slingshot, except instead of a rubber band, the spacecraft gets pulled by the invisible force of a planet's gravity. As the planet travels along its orbit, its gravity grabs the incoming probe, drags it along for a bit, hands over some of its own orbital energy, and then flings the probe forward with a huge free speed boost. Using this trick over and over, engineers managed to cut the travel time from 30 years down to just 12. NASA knew this chance would not come again for generations, so they built 2 identical spacecraft with as much backup as possible. Extra computers, spare thrusters, and duplicate communication systems, just in case something failed along the way. Voyager 2 actually left Earth first in August of 1977 on a longer and slower route designed to swing by all 4 giant planets. Voyager 1 launched 16 days later, but it took a shorter, faster path. Its job was to catch up with its twin and take a close look at Jupiter and Saturn, along with their biggest moons. Because it was moving faster, Voyager 1 actually overtook Voyager 2 before either one even reached Jupiter. What they sent back changed the way scientists understood the solar system. Everyone expected Jupiter to be a boring, lifeless ball of gas. Instead, Voyager 1 found wild, violent storms. It captured a long series of photos that were later put together into a time-lapse video back on Earth. For the very first time, people could see that Jupiter's atmosphere was not some frozen picture, it was alive, full of swirling jet streams, spinning vortices, and raging storms. And on Jupiter's moon, Io, astronomers spotted something nobody expected: active volcanoes shooting out plumes of blue gas. Next up was Saturn, with its huge system of hundreds of rings. This is the point where the 2 probes' paths split apart, and it was done on purpose. Voyager 1 was sent on a course that would take it extremely close to Titan, the only moon in the solar system known to have a thick atmosphere. Titan's gravity was strong enough to completely bend Voyager 1's path, throwing it up and out of the flat plane where all the planets orbit, and sending it off into deep space forever. That meant giving up any chance of visiting Uranus or Neptune. Voyager 2, on the other hand, kept going on the grand tour, and it remains the only spacecraft in history to have visited both ice giants. As Voyager 2 got close to Uranus, it discovered something bizarre. Not only does Uranus spin on its side as it orbits the sun, but its magnetic field is tilted a massive 59 degrees away from its spin axis, and the center of that magnetic field is not even lined up with the planet's core. To put that in perspective, Earth's magnetic field behaves roughly like one giant bar magnet, tilted only about 11 degrees from our planet's spin axis, and it comes from deep inside the Earth. Uranus is far stranger. Its magnetic axis is skewed by almost 60 degrees and badly off-center. Because of this, as the planet spins, its magnetic shield does not rotate smoothly like ours does. Instead, it wobbles and swings wildly through space. The probe then pushed onto Neptune, where it measured the strongest winds anywhere in the solar system, gusting up to 2,400 kilometers per hour. If winds that fast ever hit Earth's atmosphere, they would be moving faster than the speed of sound. They would not just rip roofs off houses, they could tear apart buildings, vehicles, and entire towns. Like a hurricane so powerful, we do not even have a category for it. After the Neptune flyby, Voyager 2's cameras were switched off. A year later, in 1990, right after taking the now famous pale blue dot photo, Voyager 1's cameras were turned off too. There were no more planets left to photograph, and every single watt of power had become far too precious to waste on pictures. From that point forward, the real value of these spacecraft shifted to their other instruments, the particle detectors, the magnetometers, and the plasma sensors. These are the tools that can sense invisible radiation and magnetic fields, sending back data that no telescope on Earth could ever gather on its own. The cameras are dark now, and both spacecraft are drifting through the freezing empty space between stars. And yet, even after almost 50 years, priceless scientific data from the very edge of our solar system is still arriving here on Earth. So, let's get back to that big question. How are we even able to hear them? To understand this, you need to look at the hardware inside these machines. All 6 onboard computers on each Voyager combined only have about 68 kilobytes of memory. That is less memory than the tiny chip inside a modern car key fob. The phone sitting in your pocket right now is millions of times more powerful than the entire flight computer system on Voyager. And all the data gets stored on an old-fashioned 8-track digital tape recorder, the kind of technology you would expect to find sitting in a museum today. But the most jaw-dropping part is how the communication actually works. Each spacecraft sends its data back to Earth using a transmitter that only puts out around 20 watts of power. That is roughly the same amount of power as the small light bulb inside your refrigerator. And remember, the Voyagers are now more than 24 billion kilometers away from us. A radio wave, even moving at the speed of light, the fastest speed anything in the universe can travel, takes over 22 hours just to cross that distance. Over such an unbelievably long trip, the radio signal spreads out across a massive area of space, and only an incredibly tiny fraction of the original signal ever makes it all the way to Earth. By the time it arrives, the signal's strength has dropped to a fraction of an attowatt, a unit of power so small I had honestly never even heard of it before. To put a number on it, we are talking about less than 1/1,000,000,000th of a single watt. It is a radio whisper so faint that without enormous antennas, it would simply vanish into the background noise of the universe. So how do engineers manage to pull such a weak signal out of all that cosmic static? The answer is right here on Earth. NASA runs something called the Deep Space Network, made up of 3 sites with giant 70-meter radio dishes, located in the deserts of California, Spain, and Australia. They are spread out around the globe on purpose, so that as Earth spins on its axis, at least one of these dishes is always pointed toward the distant probes. These huge dishes gather up faint radio waves across their enormous surface area and focus them down into a single point. The problem is, a dish that big picks up everything: radiation from faraway galaxies, background noise bouncing around Earth's atmosphere, and even electronic noise generated by the equipment itself. So how do you separate one single, extremely weak signal out of all the noise? NASA engineers use a 3-step filtering process to do it. First, they have to block out radio interference coming from Earth itself, things like cell towers, radar systems, and satellites. That is exactly why the Deep Space Network stations are built out in remote deserts, far away from cities, and why they operate on specially reserved radio frequencies that nobody else is allowed to use. Second, they need to filter out radiation coming from other stars and galaxies. To do this, the 70-meter dish is built to be extremely directional, meaning it can lock onto one tiny, precisely calculated patch of sky and ignore everything else around it. On top of that, engineers already know the exact base frequency that Voyager broadcasts on. But because the spacecraft is moving so incredibly fast, that frequency keeps shifting due to something called the Doppler effect. You have probably noticed this with an ambulance siren. When it is driving straight toward you, the pitch sounds high, but the moment it passes and starts driving away, the pitch suddenly drops lower. That happens because a moving object stretches or compresses the waves it gives off. Since Voyager is racing away from Earth, its radio waves get stretched out and the signal's frequency shifts lower. NASA's computers calculate exactly how much that shift should be in real time, and then tune the receivers on Earth to match that exact shifted frequency, which helps filter out most of the leftover cosmic noise. But there is a third problem, and it is a sneaky one. Even the equipment itself generates noise just from being warm. The random jittering of electrons inside metal components creates a kind of background static called thermal noise. If nothing were done about it, this internal hum from the hardware would completely drown out Voyager's already faint signal. To fix this, engineers cool the most sensitive parts of the receivers down to nearly absolute zero. This drastically reduces the internal noise coming from the electronics themselves and allows engineers to pick out a signal that is weaker than almost anything else around it. In case you're wondering, absolute zero sits at about minus 273 degrees Celsius, the coldest temperature that is physically possible, the point where the random motion of atoms is reduced about as close to zero as it can get. Only by combining remote desert locations, incredibly precise antenna aiming, and extreme cryogenic cooling is humanity able to catch this unbelievably weak whisper coming from the edge of our solar system. It is exactly these carefully decoded signals that helped scientists explain the mystery we started with. Why does space seem to thicken as the probes leave the solar system behind? Scientists originally guessed that the transition into interstellar space would be smooth, just a gradual fade into emptier and emptier space. But the actual boundary of our solar system, known as the heliopause, works very differently. Our sun is constantly blasting out a stream of charged particles called the solar wind. The stream blows outward in every direction, forming a giant protective bubble around the whole solar system called the heliosphere. But the space between stars is not actually empty either. It is filled with cold plasma, gas, and dust left behind from ancient supernova explosions. When the solar wind reaches the outer edge of the heliosphere, it runs straight into this interstellar material. This creates a chaotic border zone, with the solar wind pushing outward from one side and the interstellar plasma pushing inward from the other. Right at that meeting point, particle density jumps up sharply. As of today, in 2026, both spacecraft have long since crossed this boundary and are now sailing through the cold, empty space that exists between stars. But their time is running out. Right now, their biggest enemy is not space dust or radiation. It is simply running out of power. Out where the Voyagers are, the sun still looks like a very bright star, but its light is far too weak out there to be useful for solar panels. Instead, both spacecraft run on something called RTGs, or radioisotope thermoelectric generators. Despite what a lot of people assume, these are not tiny nuclear reactors. There's no controlled chain reaction happening inside, no complicated electronics, and no moving parts that could wear out or break after 50 years. The design is actually beautifully simple. Inside sits a tough capsule containing plutonium-238. This material naturally decays over time, constantly giving off a huge amount of heat, which keeps the whole capsule extremely hot. Wrapped tightly around that capsule are thermocouples, thin plates made from special semiconductor material. When one side of these plates touches the scorching hot plutonium capsule, while the other side faces the freezing vacuum of space, that extreme temperature difference generates an electric current all on its own. But there is no cheating physics here. Plutonium-238 has a half-life of 88 years, which means it is constantly decaying and giving off less and less heat over time, and the thermocouples themselves also slowly wear down. As a result, both spacecraft lose a little bit of power every single year. Out of the original 11 scientific instruments carried on each spacecraft, only a handful are still switched on today. Voyager 1 has just 2 working instruments left, and Voyager 2 has 3. To keep the probes alive as long as possible, NASA engineers have been remotely shutting systems down one by one, constantly making incredibly difficult decisions about which instrument to sacrifice next. That raises another interesting question. How does the spacecraft even receive commands from Earth in the first place? It works through that same deep space network, just running the opposite direction. While the probe whispers back to Earth with only about 20 watts of power, the giant 70-meter dishes on Earth send out a powerful, tightly focused beam carrying tens of thousands of watts. As that signal travels across those same 24 billion kilometers, it also weakens massively along the way. But each Voyager has its own large 3.7-meter dish permanently aimed at Earth with pinpoint precision, working like a collecting bowl that gathers up whatever faint scraps of that signal manage to arrive. Even so, the connection speed is painfully slow, only about 16 bits per second. Because of that, sending a single command up to the spacecraft can take hours, and confirming that it actually worked can take almost 2 full days. It was through exactly this kind of slow, painstaking process that engineers had to send a command to shut off even the heaters that keep the instruments from freezing solid. Amazingly, this old electronics has kept working even in the brutal cold of deep space. But the power keeps draining with no way to stop it. Sometime in the next few years, likely by the early 2030s, there simply will not be enough power left to keep the transmitters running at all. At that point, engineers will send one last command, and then the connection will be gone for good. Back here on Earth, there will be complete silence. But for the Voyagers themselves, losing contact with home will not be the end. It will only be the beginning of an endless journey through the universe. Once the transmitters finally shut off, the two spacecraft will no longer function as scientific instruments, but they will not simply become space junk either. Bolted onto the side of each spacecraft is a small package known as the Golden Record, a gold-plated copper disc carrying sounds from Earth, along with music, photographs, and greetings recorded in dozens of different languages. Engraved on its cover is a map showing exactly where our planet is located. It is essentially a message in a bottle tossed out into the endless ocean of space, meant for someone we will most likely never meet. Once the signal is lost for good, their true silent journey through time will really begin. In roughly 300 years, the two probes will reach the inner edge of the Oort cloud, a huge shell made of icy objects surrounding our entire solar system. It will take them somewhere around 30,000 years just to drift all the way through it and finally leave the outer edges of the solar system behind for good. Around 40,000 years from now, they will make their first close passes near other stars. By that point, tiny space dust will have badly pitted their outer shells, their antennas will be bent out of shape, and radiation will have darkened their metal surfaces. But the sturdy aluminum casing protecting the golden records should keep them in nearly perfect condition the whole time. About 5 billion years from now, our sun will begin to die. It will swell up into a red giant star, and Earth will either be completely swallowed by it or scorched into a lifeless, burnt husk. But by then, the Voyagers will already be long gone, far away from all of that. Around this same distant point in time, another massive event may take place, the collision between our Milky Way galaxy and the neighboring Andromeda galaxy. If that collision really happens, gravity will completely reshuffle the paths of billions of stars. Nobody can say for certain where the two tiny Voyager probes will end up in all that chaos. They might end up drifting quietly on the edge of a newly merged galaxy, or they could be flung even further out into the cold, empty gap between galaxies. Around 10 trillion years from now, even the longest-lasting stars in the universe, the small, dim red dwarfs, will finally burn out completely. Space will fall into permanent darkness, marking the start of what scientists call the era of matter decay. At that unimaginably distant point, even the individual atoms making up the spacecraft's shell and the golden disks will slowly start breaking apart. The basic laws of physics will, in a way, quietly erase the Voyagers from existence, atom by atom. But until that very last atom finally breaks down, these two small, battered pieces of 1970s machinery will keep drifting silently through this void. They will remain among the most lasting things humanity has ever created, standing as proof that once, somewhere on a small, pale blue dot, there was life that looked up at the night sky and dared to reach for the stars.